Bismillah ar-Rahman ar-Rahim. Today we will talk about another interesting problem that will be solved using definite integrals. We hear the word average, mean, average. Average of students, for example, average of the grades of students. Okay, so we understand the meaning of the average of discrete points. Recall this. If you have some readings like x1, x2 up to x infinite number of readings, then what is the meaning of the average of this? The average will be x average is the summation of these readings divided by the number of them, which is in this case n. But if we ask ourselves, if we have infinite number of readings that we represented by a function, for example, we have, if this is the y coordinate, the y-axis, and this is the x-axis, and we have a function y equal to f of x over a specified interval ab. The question is, can we find the average reading of this function? In the function here, we have the images of infinitely many points between a and b. So the interesting question, what is the average value of the function here? This kind of average will be answered by the following argument. Okay, so what is our question here? How to find the average value of a continuous function given y equal to f of x over a specific interval. Now, let us motivate the formula to find the average. So let us just draw some continuous function and then see how to find the average between a and b, the average value of that function between a and b. So simply this is what we will do. We will assume again this is the y-axis and this is the x-axis. So this is the xy coordinate like this. Assume we have a continuous function like this, okay? And we have a specific interval here. We have it from a to b. Now we discussed many problems related to definite integrals. We discussed the area problem, the volume problem, etc. Another one. How to find the average value of the function here, y equal to f of x. We have different readings. We have f of a. If you have a point here, then we have the image of that, the image, the different images we have. So different y values we have. What is the average of this? What is the average value? Okay. As usual, we will do the following trick. We will partition the interval. So this is x0. Then we have here x1. We have here x2, etc. We have here up to, let us say, xi minus 1, xi, and so on. You just move up to what? The last one here, which is b, it is xn. So again, we are partitioning this interval into sub-intervals with equal width. So we are taking uniform partition. What we will do here, we'll come to the first sub-interval and we will take a representative for the function. For example, I can take the image at the left point to be the representation of the function over the first sub-interval. I can take it to be the end one, so I'm approximating by taking the value at the end. I can take it at the middle here, different type of approximation. So what happened here? The average value of the function, I will denote this by AVE of f. Okay, something like this, just as a notation, average of f or f average. Okay, different notations are used for average value. We may use this notation. We may use also something like this, f average. Let us say this one, for example, f average. This is approximately equal to what? Now, what I will do, I will add these sample points. So I will take f of x1. So I'm choosing here the endpoint to be our sample point in the first sub-interval, plus f of x2 plus f of xn. Now we're supposed to sum up all values, but what we are trying to do now, we are taking only sample of points. So we are taking sample of points that explain what's happening for the function between a and x1. We take other sample points that explains what's happening between x1 and x2. So we take it only the points at the end. That's why we have here what? Approximation. Now, what is n? Or what is 1 over n? If you recall how to partition a certain interval, we said delta stands for b minus a divided by n. So this width here is just delta x, which is given by b minus a divided by n. So you can easily see that from here that 1 over n is equal to what? It is 1 over b minus a times delta x. Simply you just solve for 1 over n. So we need to divide by b minus a, both sides. So that will be delta x over b minus a. Now going back to the formula for f average we are trying to derive now. What is f average then? F average will be approximately equal to. Now I will replace 1 over n by the quantity here, 1 over b minus a times delta x. So what do we have at the end? We have something like this. 1 over, I will write it this way, b minus a times another thing. Here we have what? Summation of, let me write it without this, so sorry for that. So let us try to rewrite it this way. We have bracket like this. So we have f of x1 plus f of x2, okay, plus up to f of xn. And then this is multiplied by delta x. I'm replacing 1 over n by 1 over b minus a times delta x. I just rearrange it. This is 1 over b minus a and this is delta x. Fine. Look for this summation here. This is exactly equal to what? 1 over b minus a summation of, you can write it from I equal to 1 up to n. This is f of xi multiplied by what? Delta x. Fine. Until now we are approximating the average of the function. But to make it exact, we need to push n to go to infinity as usual. So I need to take the limit as n goes to infinity. Meaning I'm increasing this number of points to be infinite. So it's like we are evaluating the function at each single point. So what do we have here? This will be equal to 1 over b minus a. I will take the limit as n goes to infinity of this summation here, summation I equal to 1, up to n. This is f of xi multiplied by what? Delta x. Now, look for this limit here. What does it represent? By definition of a definite integral, this is nothing but 1 over b minus a. This limit summation stuff here, it is just the integral from a to b f of x dx. So, this will give me exactly what? This will give me exactly the average of the function. Until now, here we have approximation. So this is f average is, of course, approximately equal to this. Once you take the limit, f average will be exactly equal to this. So at the end of the day, we have f average is given by this. Of course, we are talking about the average of the function over the interval a, b, assuming our function is continuous function. So this formula, this nice formula will give us what? Will give us the average of a continuous function over a specified interval. So we succeeded to find now the average value, not of a discrete number of points, but we have continuous reading, we have infinite number of points, and we were able to find exactly what is the average of that function. We will see now how to apply this to solve some exercise about average value of the function and what does it mean geometrically. That will be done in the second point. Now, after deriving the formula for finding the average, let us apply it in this exercise. The exercise says, find the average value of the function, which is a continuous function for sure, 1 plus x squared, on the interval minus 1 to 2. Okay, I remind you with the formula we get, we said the average value of the function, so it is f average is equal to, it's 1 over b minus a times the integral from a to b. This is f of x multiplied by dx. Okay, so we just apply the formula here. We have a equal to minus 1, we have b equal to 2, we have the function, so this is equal to 1 over, now b minus a is 2 minus 1, that is equal to 3. Integral from, we have it from minus 1 to 2, f of x is just 1 plus x squared, and we are integrating with respect to x. So that's the formula we have, and we need now to apply only the techniques we did for integrating and evaluating the integral we have here. So it is 1/3 times, now let us integrate, we get here x plus x cubed over 3, and this is evaluated from minus 1 to 2. And if you just substitute here, simply you get the following, 1 over 3 times what? Now if we substitute 2, this will be 2 plus what? 8 over 3. That is the first one. Then we have minus and then we substitute minus 1 to get here minus 1 over 3. Okay? Now, simplifying this, we get the following. We have 2 minus 1, that is equal to 3. And we have 8 over 3 minus 1 over 3. That's 9 over 3. That's another 3 we have. And this is all divided by 3. So this is equal to what? This is equal to 6 over 3, which is equal to 2. Okay? So the average value of the function f of x, 1 plus x squared, from minus 1 to 2 is equal to 2. Now, let us look at this from the geometrical point of view. What does it mean? Look here. We have the graph of the function, which is, can see easily, parabola opening upward. We have 1 plus x squared. If we just partition this one into 1, 2, 3, 4, etc., this is minus 1, let us say minus 2, minus 3. Then we have also here 1, 2, 3, 4, 5, and so on. If you go minus 1 to 2, minus 1, this will give us minus 1 squared, that's 1 plus 1, that's equal to 2 somewhere here. We have minus 1 and 2, so this point is minus 1 and 2. If you substitute 0, you get the value is equal to 1. And then you move up to 2. At 1, it will be again equal to 1 plus 1, that's 1 and 2. Okay, it's symmetric around the y-axis. And at 2, this is equal to 1, 2, 3, 4, 5. So this is the point here, 2 and 5. This is the point 2 and 5. So we have a parabola coming this way, continuing up to the last point we have here. Fine. This is the graph of y equal to f of x, which is x squared plus 1. Now, the average is equal to 2. What does it mean the average is equal to 2? Okay, y is equal to 2. What is y equal to 2? So, we have here, you see, at minus 1, we have the value is equal to 2. After minus 1, it is something less than 2, and so on. Up to 0, this is 1. So, this is another value, a third value, and so on. You have infinitely many values. This result says that the average of all of these values of y is here. Exactly at y equal to 2. So this value here is giving you the average reading of all these values. And a very interesting point now will come is the following. Assume we have discrete data. For example, assume we have 3 readings. x1 is equal to 10. x2 is equal to 20, okay? x3 is equal to 60. 10, 20, 60. Then, what is the average of these 3 values? The average is, x average is equal to, you add them, so you have 10 plus 20 plus 60, and then you divide by the number of points. So what do we have here is 30 plus 60, that's 90, divide by 3, this is equal to what? This is equal to 30. Fine. My question is the following. Do we have any guy here getting 30, which is exactly the average? 10 is not 30. 20 is not 30. 60 is not 30. So nobody is getting what? Exactly the value of the average. The next important point we have here from this nice result we get, we'll say that always if you have continuous function, always there is one guy who is getting exactly the average. So we will have a nice theorem called the mean value theorem for integrals that says whenever you have a continuous function, you evaluate its average. Of course, the average is there. Then always there is a point, at least one, between the A and B whose image is exactly equal to the average. You see, this interesting result is not hold for discrete data. But if you have continuous data, always you have someone getting exactly the average. That will be called the mean value theorem for integrals, and that will be our next point. Okay? Now, before we move to the mean value theorem for integrals, let us refresh our memory with the mean value theorem for derivative. What does it say? You remember in calculus 1 we discussed the mean value theorem of a derivative that says if you have a continuous function over the closed interval AB, this is B and this is A. So if this is continuous over the closed interval AB and it is differentiable over the open interval AB, then always you have the case like this. always there is a c such that f of prime of c is equal to what? F of b minus f of a divided by b minus a. We said if f is continuous over the closed interval, it is differentiable over the open interval, always this will be guaranteed by the mean value theorem for derivative. What does it mean geometrically? In that case, we said we have a secant line joining these 2 points like this. So this is what we have. We call this one the point B and f of B. And we call this one A and f of A. Of course, I'm talking about the xy coordinate, and this function, I called it f of x. Fine. What does it mean, the mean value theorem for derivative first? It says between A and B, you're supposed to have at least 1 point. Who is the derivative? Which is the slope of the tangent line? Is exactly equal to what? Is exactly equal to the slope of the secant line we have here. For example, you can talk about this C here, whose tangent is parallel to this line. Another one, maybe you can have it here, so the tangent line here is exactly parallel to that line. So we have different values of C's. Whose derivative, meaning the slope of the tangent line, is exactly equal to this quantity. So it means there is at least one line which is tangent to the curve and parallel to what? To the secant line. Fine. Now, we will use it to prove the mean value theorem for integrals. Here, the mean value theorem for integrals says what? If you have a continuous function over the closed interval, then always there exists a number c inside this interval such that the value of that function at c is exactly equal to the average of the function. We have seen an example that says, and many examples, that sometimes if you have discrete data, you may end up with an average and nobody is getting exactly equal to the average. Nobody is getting exactly the average. I gave you an example, 10, 20, and 60. The average is 30, but nobody is getting 30. Another example, you take, for example, someone is getting 0, the other one is getting 100. The average is 50, but nobody is getting 50. This theorem says, for continuous function, it is not possible. Always, there is some guy called the C, for which the value of that, his grade is exactly equal to the average. His reading or its reading is exactly equal to the average of the function. Or you may look at it from different point of view, that the integral which represents the net area can be represented by one rectangle only. Can be represented by one rectangle only. Let us see this in the previous exercise we did. The geometrical meaning. So before I go to see the application of that, let me say something about the result itself here, how it is proved. So let me define something here. The proof of this theorem is simply by applying what we call it the mean value theorem for derivative. That's why I recall the mean value theorem of derivative. So let us define, if we have a function f, let us define capital F like this. We define it like the integral from a to x, and I will say here f of t dt. This is a well-known function for us now. We introduce this function when we talk about the fundamental theorem of calculus, and we say this is a function of x. Okay, not only that, if the function f is continuous, then this function is continuous. Not only this, it is also differentiable over a and b, the open interval a and b. More than continuous, it is differentiable over the open interval a, b. So all requirements we need for mean value theorem of derivative is there in this function. Continuity is there, differentiability is there. So we can apply the mean value theorem of derivative. Okay, the mean value theorem of derivative says what? It says, so now this is, I will say some comments about this. The first one, this f is continuous, I will say, on the closed interval AB. Okay? Not only this, this function is differentiable on the open interval AB. Fine. It is continuous, it is differentiable. So by mean value theorem of what? I will just derivative, okay? So the result we have in calculus 1, by the mean value theorem of derivative. What do we have? There is at least one c, there is a number c. What is that number? Okay, let us say C in between A and B. There is a C at a value of a number C inside this interval AB, such that what? Such that f prime of C is equal to f of B minus f of A divided by B minus A. This is exactly the mean value theorem of derivative. Okay, let us calculate this. What is f prime of C? What is the derivative of this function with respect to x? The derivative by fundamental theorem of calculus is just a small f of x. So when you substitute C, you get what? You get f of C equal to. Now, let us look for the right-hand side. We have f of B. What is f of B? It is the integral from A to B, f of x dx, minus f of A is the integral from A to A, f of x dx, isn't it? This is what we have. Divided by B minus A. I'm just applying the mean value theorem of derivative. Now, what is this? By the properties of integral, the value here is equal to 0. Now, let us rewrite this. What is that? This is equal to, I will just write it this way, 1 over B minus A times the integral from A to B, f of x, what? dx. This is equal to f of C. So there is at least one C whose image is equal to this quantity. This is guaranteed by the mean value theorem of derivative. Now, what is this? The right-hand side, you can recall the definition of the average value. This is nothing but f average, and this is equal to f of C. So, meaning there is at least one C between A and B whose image is exactly equal to the average. Now, let us come back to our example. So, let us say example number 2 says, find the number C. It could be one number, it could be more than this, C, such that f of C is equal to f average, where we have f of x is just x squared plus 1 on the interval we chose before, minus 1 to 2. Okay? This is what we have in example 1. So, what is the average of this? F average. We said it is just 1 over 3. If you remember the integral from minus 1 to 2, x squared plus 1 dx. And we found this to be equal to what? To be equal to 2. We did the calculation here. Now, we need the value of C for which the f of C equal to f average. So what should we do? We evaluate f of C. F of C is equal to f average. It means C squared plus 1, I'm replacing this by C, equal to f average. F average is equal to 2. So, I get two values actually. C squared will be 2 minus 1, that's equal to 1. And in this case, I have C is plus or minus 1. Clearly, if you take the C equal to 1, you substitute here, you get the value is equal to 2. What is 2? 2 is the average of the function over that interval. If you take minus 1, similarly, you get this is equal to 2. So we have 2 points whose images equal to the average of the function. Now, let us look. Of course, these 2 points belong to the interval minus 1 to 2. So we have 2 values of C's. 2 values of C that satisfy what? The mean value theorem of integrals. Now look at it. Looking at this geometrically, this is what we have. Again, I will just sketch the graph of this. I have minus 1. Let us say this is 1. So I have this is minus 1 and 2 somewhere here. This is minus 1 and 2. Then the graph is coming this way. And then it will continue up to 5 somewhere here. So this is 2 and 5. Say like this. This is x. This is y. This is the graph of y equal to x squared plus 1. Now, look at this interesting result we have here. This is minus 1, and this is exactly equal to 2. Now, we have 2 things. We have the integral from minus 1 to 2 of x squared plus 1 dx. We said this is exactly equal to, look here, this is exactly equal to f of c times b minus a. So meaning, this is exactly equal to, according to our calculation here, it's exactly equal to, for example, f of 1 times b minus a, which is 2 minus 1, something like this. Now, what does it mean geometrically? Look for the left-hand side here. The left-hand side in this specific graph represent the area under the curve. Now, the mean value theorem for integral says always you have a c between minus 1 and 2 whose image is exactly equal to the average. Meaning, you see here the average is exactly equal to 2, the average of the function. So this altitude here is representing what? The average of the function. Now, the mean value theorem says always you can find only one rectangle whose area, look here, the area of this rectangle here is exactly equal to the area under the curve. So you can represent the area under the curve by only one rectangle. Okay, this rectangle has two images in this case, I mean pre-images. You see here, we have it at 1, the altitude is 2, and we have it at minus 1, the altitude is 2. So we have two representatives of this image. But at the end of the day, we have the area under the curve, the total area here under the curve is exactly equal to the area of the rectangle. This will be guaranteed only by the mean value theorem for integrals. So, the mean value theorem of integrals simply says, whenever you have a continuous function, you get its average always in the x-axis between a and b. There is a point, at least one, whose image is exactly equal to the average. Or it says the net area under the curve, the net area under the curve can be represented only by one rectangle whose altitude is the average of the function. That is simply the mean value theorem for integrals. We will see only more exercise about this idea, and that is the main idea for the mean value theorem and what we call average value of the function. So we will see another exercise about the mean value theorem for integrals and the average of the function now. Now the next exercise will summarize for us the average value or the relationship between the average value of a function and the mean value theorem for integrals. Okay, the example says, let f of x equal to radical x. You are given a specific interval and you can observe that this is a continuous function over this closed interval. So everything we need about the theorem is there. The question says find the average value of f on that interval. Then by the mean value theorem find the c such that f average equal to f of c. Then illustrate the result geometrically. So that's what we need to do. So let's come to part A. Part A, we need to find what? We need to find the average value of this function. So what should we do? The average value of the function, we apply the formula we derived. It says 1 over b minus a, the integral from a to b, f of x dx. Now, applying this for the specific function we have and the given interval we have, it says 1 over, we just substitute for b and a, so it is 1 over 4 minus 0, that's 1 over 4. I'm substituting 4 minus 0. Integral from, this is from 0 to 4, and the function is just radical x dx. Okay, fine. This is equal to what? It's 1 over 4 times, now let us substitute here. Integrate and then substitute. We have x to the power 3 over 2 times 2 over 3 evaluated from 0 to 4. This is what we have, and this is equal to. If you take the constant out, so this is 1 over 4 times 2 over 3, and then we evaluate at 4, this is 4 to the power 3 over 2 minus 0. At 0, it's equal to 0. Good. So this is equal to. Okay, this is cancelling the 2 with the 4 here, we have 1 over 6, right? Because 2 times 3 is equal to 6. Times, now looking for this as 2 squared, the 4 as 2 squared, I have 2 to the power 3, that's equal to 8. So this is just 8 over 6, or this is 4 over 3. Fine. So this is the solution of part A. That says find the average value of this function over that specific interval. We are done. The second part is the application for the mean value theorem that says always this value can be attained at a point C. So what is that C? For find the C that satisfies the mean value theorem, or find the C such that f average equal to f of C. So simply what they need to do is just substituting C here. So I will solve it by saying that radical C is supposed to be equal to 4 over 3. So this will give us C is equal to 16 over 9. 16 over 9 is a number which is less than 2. So yes, this number is inside the interval 0 and 4. So this is the C that satisfies the mean value theorem. The last part says explain this one geometrically. Explain this one geometrically, it means find a rectangle whose area is exactly equal to the area under the curve. Okay, let us see how to do this. So let us sketch the graph of the function, looking for the average of that function, and then we search for that rectangle whose area is exactly equal to the graph or the area under the graph of radical x. Okay, so let us try to sketch the graph of the function first. So this is what we have. Okay, we have y equal to radical x, so this is 0 and 0. Let us say this is 1, and assuming this is equal to 2, this is 1. Let us say simply this is 2, 3, and 4. So we have another point 4 and 2 somewhere here. Okay, this is just a sketch of the graph. At 1, it's also equal to 1, the radical function. So we have a curve joining these points like this, and it will continue for sure. Okay, we are talking about the interval 0 and 4. So what I will do, I will stop here, exactly at 4. This is the value here. So I'm talking about y equal to radical x. So there is a y equal to radical x here. This is y equal to radical x. Now what does what we did here mean? Let's look first for the average of the function. What is the average of the function? The average of the function is exactly equal to 4 over 3, which is 1 and 1/3. 1 and 1/3, somewhere here, if this is 1/2, so this is 1/3, so this is the value of the function here. This is, let us say, 4 over 3. This altitude here. So this line is y equal to 4 over 3. So this is exactly 4 over 3. So this is 1 and this is 2. Fine. Now what does it mean here? The second part says this value here, so supposed to be attained at a certain point. Of course, this is not accurate graph. So this value here is somewhere here. This point supposed to be 16 over 9 according to our calculation. Now, what is the rectangle whose area is exactly equal to the area under the curve? Look for this rectangle here. Whose width is what? 4. Or the length here is equal to 4. And the altitude is equal to 4 over 3. So the area under the curve, y equal to radical x, is exactly equal to the area of this rectangle. You see here, this is the area under the curve. So this region is common between them. This is supposed to be equal to this. Of course, this is not an accurate graph, but it will show the idea. The idea here that is gained by the mean value theorem, it says this area of the rectangle we are drawing here is exactly equal to the area under the curve. That is the result of the mean value theorem and the formula for finding the average. I will show you another application or another example about mean value theorem in the following exercise. Now let us see another way to represent a question about the mean value theorem of integrals. The question here says if f is continuous, and it is not a secret because we need this one in the theorem. We need continuity of the function. So f is continuous and we are given the integral part here which is equal to 8 of that function, and the question says show that f takes on the value 4 at least once on that interval. We are getting information about the integral of the function, but we need to deduce something about the value of the function. And the only thing that relates these two things is the mean value theorem of integral. Let us see how to apply it. Now let us see first what is the average of this function. What is f average over this interval? What is f average over the interval 1 and 3? By the formula it is equal to 1 over, look here, it is 3 minus 1 times the integral from 1 to 3 f of x dx. So we Step number 1 says the average value of this function is 1 over 2 times 8, which is given. So this is equal to 4. That is the first point we need to figure out here. The average value of that function over this interval is equal to 4. Now, since this function is continuous, the mean value theorem of integral says always there is a c whose image is equal to the average of the function. So we will conclude the result here by mean value theorem, mean value theorem here of what? I will specify it, of integrals. What is the result? There is at least one c, at least one value c, one number c, and this number c is what? Let us write it here, one number c that belongs to the interval 1 and 3, because we apply it in this interval. Okay, what is the property of that c? For which f of c is equal to f average. And what is f average? In this case, the average value of the function is simply we calculate it to be equal to 4. So what does it mean? We have at least one c between 1 and 3 whose image is exactly equal to 4. So the value of the function is equal to 4 somewhere between 1 and 3, at least one. At least one time it is equal to 3. This is guaranteed by the mean value theorem. So as a summary now, we started with discrete data and we were able to calculate the average. We use it as a guideline to derive a formula for the average value of a continuous function by taking sample points and push the number to go to infinity. And then we observe that always if you have continuous function, then we have one guy whose value is exactly equal to the average, which is not happening all the time when we have discrete data, finite number of data. If you have continuous data, then always you have a representative for the average of that function. This is the mean value theorem and average value of a function, and that's it for this material.